And then let's move to the R code, which is already prepared for us. And let's see how it works. This exercise could be done also in Excel, but I decided to use R. So this is our R code. Let me first read, open an R window. Okay. So my R code, here it is. So first of all, there are some comments, and you have the address of a file on my website, which you can find more details on pairwise comparison. There is extensive information in this file. It's also the file, it's a zip file, so you have documents explaining the theory and another proposed exercise. This is just to give you an hint if you want to get more information on this. But again, this is not part of what I asked at the exam. So, first of all, we have to define these utility functions that are given by the PDF in an analytic way in order to define what is the utility of each alternative. Let's look at the first one. The first 5 lines refer to the computation of the utility of, in terms of indicator 1, so you see utility 1, which means utility indicator 1 of each alternative, 80, 90, 100, 110, 120. Okay, so as you remember, in this range we have a linear increase of the utility. So you see that here the value of the utility for each alternative is computed in this way. First of all, the linear increase, let me make a sketch just for the first one in order to clarify. It's trivial, but so this is U1, and it's given in the PDF U1 in this way. From 0 to 30, it's flat and equivalent to 0, as you remember. And then there is up to 150, a linear increase to 1. So you have this linear increase. Now we have to compute the utility of 80, which is somewhere like here, 80. Okay, so first we have to compute, and here we have a span of 50. First we have to compute this slope, and the slope is given by 1, which is the height from 0 to 1, divided by the distance on the horizontal axis, which is 150 minus 30. So 1 divided by 150 minus 30, multiplied by 50, the span, 80 minus 30. Very simple, it's linear interpolation. The same thing for the other 4 lines. So I think there is not much to say here. And these 4 lines, you can copy and paste them in R. Good. So if you are curious, you want 80. If you are curious, this is U1 80, and this is U1 120. Very good. Okay, same thing for the other utility functions. Okay, this is U2. And of course here it's a bit different because we start from 1. These are decreasing functions. And you see that U2, we have 1 minus, okay? And then U3 and U4. Okay, so let's copy them. Good. Any questions so far? Good. Okay, now, just in order to, let's create a matrix of these values of the utility. So, first of all, let's create a vector which gives the utilities, the 4 utilities for the design flow equal to 80. So copy, paste, and then if you write U80, these are the 4 utilities. Now let's take the other utilities. Copy, paste. Okay, good. Now let's have a look at these utilities. U80, okay, U90. So let's see what is the landscape here. No, the landscape, I mean the configuration. Are the values of these utilities reflecting what is reflecting our expectation? So remember that the first indicator in these 2 vectors is economic benefit. The second is fisheries. The third is landscape, and the fourth is fruition of downstream reach. So we are expecting, what we see here is that the first indicator increases, passing from 80 to 90, which is fine, and the other indicators decrease, which is fine, okay? And we expect the same if we go to 100, 110, and 120. These kind of checks, try to get used to them because they are very quick to perform, and you know, when you make a design, you don't want to make mistakes, and the usual way to avoid them, the most efficient way, is to make some quick checks for any step, and rather than going back to the code and saying like, okay, what I have written here, is it correct? Or this is of course a way of checking, meaning looking back at your computation, at your codes. But another way of checking is by looking at the results. If they match your expectation. This kind of check usually avoids that you make big mistakes. Okay, if you continuously match your results of your design activities with your expectation, usually you avoid big mistakes, and these are the kind of mistakes that you really want to avoid, because of course if you make a small error, very often it is included in the uncertainty range, and then you get, as an engineer, you get a safety factor which protects you. But if you make a big mistake and you don't realize it, this is very bad. Okay? And this is the same reason why I insist on the orders of magnitude. If you get a design rainfall that is 15 meters in 1 hour, it's of course wrong because it's impossible. But you have to recognize it, and to recognize it, you have to get used to orders of magnitude. Or you estimate a peak flow for the Po River, and it's 200 thousandths cubic meters per second. It's impossible. The max flow that is conveyable by the Po River is about 20, maybe from 15 to 20,000 cubic meters per second. So if you get 200,000, it's too large. Okay, so let's go back. Now, these are our utilities, and if you look at the code, then all of these utilities are put into a matrix. So let's copy it, copy, and let's paste it. Okay, so if you clear the screen and you type U, you have all the utilities, which is nice to see. And it's, this is the place, the stage where you could really quickly make the check that I did before. You look at the matrix and you understand that is indeed something reasonable. Okay, good. So far we didn't do any computation, just putting data into R. Okay, let's move forward. Now, we have to define the matrix of the pairwise comparison, how it works. I told you something last lecture, but let me just give you some more details on the theory. What is the purpose of pairwise comparison in this case? The purpose is to determine the weight of each indicator. And you have 4 indicators, as I said. Let me write on the blackboard. And the first E1 is economic. E2 is fishery. The third, E3, is landscape. The fourth, I4, is tourism. What is the purpose of the weights? I said that we have to determine weights. The purpose is I have a utility matrix, which is displayed, I think, no, it's not here. So for each design, if you look at the rows, for each alternative, we have 4 utilities, but we don't have a score. If I had to give priority to these 4 alternatives, the 5 alternatives, to these 5 rows, for me, if I look at the matrix, it's impossible, because I see that some indicators give more weights to one and some other give more utility to others. And I need to combine, for each alternative, I have to combine these 4 columns, 4 utilities. And in order to combine them, it's not just enough that I sum them. This is a possibility. I give the same weight to each indicator, to each column, and I sum them. But this means giving the same weight. And of course, if you discuss with your stakeholders, there will be people saying that you have to consider only the first one, which means giving weight, all the weight to the first column and discard the other columns. You will have fishermen who will say, give weight only to the second column. And therefore you have to determine weights. Okay, and then once that you determine the weights, you can combine the 4th column through the weights. By definition, weights sum up to 1. So the sum of W is the weight I, is equal to 1. When we talk about weights, usually we assume that they have to sum to 1. And therefore we have to give numbers to these 4 indicators. And as I said, one possibility is 1, 0, 0, 0. This is one possibility. This is the option that the client, the people who pays for the plant, would prefer. If you ask fishermen, they will say 0, 1, 0, 0. If you ask the local administration, they may be interested in tourism, and therefore they may say 1 to tourism and 0 to the others. I have to find the optimal combination. But if you engage in a discussion with a lot of people and you have to decide the weight for 4 indicators, and keep in mind that they may be 10, it's very difficult to manage because this is a complex decision. And therefore, as I said, the option is pairwise comparison, which means comparing the indicators 2 by 2 and give a score, so determining a matrix. So, these are 4 indicators. I have to write a 4 by 4 matrix. I1, I2, I3, I4, and again here, I1, I2, I3, I4. This is my matrix. Pairwise comparison uses a scale in order to identify the importance of, let's say, the first indicator with respect to the second. This is a first comparison. What is the importance of economic with respect to fisheries? And this is something that is more manageable to ask to an audience, And the pairwise comparison uses a scale from I don't remember, just 1 second. I think it's from 1 to 9, but I want to be precise, so let me check. And this is the content of the file that I indicated to you. Okay, here is the scale. Yeah. 1 is equal importance from 1 to 9. 1 is equal importance, 9 is extreme importance. Therefore, if you think that I1 is extremely more important than I2, if you think that economic is extremely more important than fisheries, then you should give a score of 9. If you think that economic has the same importance of fishery, you give a score of 1. Of course, the scale is extended to numbers below than 1, because when you turn to the opposite comparison, the importance of fishery with respect to economic, if you gave 9, which means that economic in the previous comparison, in the symmetric comparison, I compare economics with fishery, I give a score of 9, which means economics is much more important than fishery. When I compare fishery with economics, I have to give a score of 1 over 9. So the scale is from 1, same importance, to 9, extremely more important, and then the scale is extended in the range 0, 1 to allow symmetric comparison. So let's then populate this matrix. First of all, in the diagonal, I have ones, because I compare the indicator with itself. Okay? And then, if I give to I1 compared with I2, if I give 9, then I have to write 1 over 9 here. Now let's compare, and this is an example, just an example that I'm building now. It's not the same example that is reported in the R code. Okay? But anyway, it's another example. So I gave a lot of importance to economic with respect to fishery. Now let's compare economic with respect to the landscape. And I may say, yeah, it's more important, economic with respect to landscape, but let's take 3. And then it means that here I have to put 1/3. Because the matrix is symmetric in a way that the symmetric position is equal to 1 divided the one that we assigned. Okay? Keep in mind one thing. If I gave to economics an importance of 9 with respect to fisheries, and an importance of 3 with respect to landscape, it means that landscape, according to my evaluation, is more important than fisheries. And this means that my evaluation should be consistent. I have to keep in mind this. When I will compare I2 with I3, I have to try to remember this. Okay, now, I1 with respect to I4 tourism. Okay, we may say, same importance. Which means that tourism is more important than landscape and is definitely more important than fisheries. Okay, now let's compare I2 with I3. Let's compare fisheries with landscape. Should be less important in order to make the evaluation consistent. How much less important, I don't know, but let's say 1 divided by 5. Which means that here I have to put 5. And then I have I2 with respect to tourism, and this should be 1 over 9, fishery with respect to tourism. So 9 here. And now it remains only landscape with respect to tourism should be less important. So I don't know, let's put 1/3, which means 3 here. This is our matrix of the pairwise comparison. Is this matrix consistent? Hopefully, but we are not sure. Of course, it could be completely inconsistent. And if it is inconsistent, it means that the overall procedure, it's not working, it's not efficient. So we need a way to check consistency, an analytic way. But before moving forward and checking consistency, let's discuss on how this matrix could be populated, because it was very easy for us, because I just populated it and you listened to me. But in a public decision, in a public consultancy, you cannot do this. If you chair this public consultancy, you should give the word to the audience and try to see if there is a way altogether to carry out this discussion. And it might be impossible, or it might turn out that the evaluation is not consistent at the end of the story. And therefore, in order to reach consistency, you can continue the discussion. There is another possible way. If you see that it's impossible to manage a collective discussion, you can split people in groups. Groups with something in common. And then, once that you got, let's say, 3 groups of people proposing 3 different matrices, then you can try either to average the resulting weights in some way, or you could try to put the 3 matrices on the blackboard and try to see if there is a way to reach consensus. This is still a delicate phase where it's your ability to reach a compromise, to seek compromise that matters. And this is something that, you know, there are suggestions for reaching compromise, and the social scientists are usually know these methods, suggestions, but at the end of the story, beware that the ability to seek compromise, it's an individual attitude, which indeed it's very appreciated in modern society. So when people talk about candidates for leadership, a thing that they look for in the CV is one thing is often the ability to seek compromise, which is a personal attitude. And as I said, in the past, for engineers was not much important, and our organization, societal organization, was more hierarchical and less transparent. Today, as you see, there is an increasing need of reaching consensus without imposing decisions from the top. It's a bottom-up approach, and therefore this is an ability that is gaining more and more importance. Keep it in mind, because it's something that you need to train. And sometimes it means that you don't have to impose what you think is correct, even if you are dead sure that you're, from a technical point of view, what you are proposing is correct, you don't have to impose it. You have to bring people to believe that it's correct, to realize that it's correct, basing on their autonomous assessment, not basing on listening to you. And this is something tricky in certain cases, but still it's also exciting, so try to look opportunities in that, because it's also an opportunity for you to exploit your ability and to give you an additional way to give your contribution and to emerge, to succeed. Okay, now, how to compute the weights? Let's suppose that the matrix, we have to check consistency, and then from this matrix we have to compute the weights. And there is an analytic procedure. We don't go into the details. There is an analytic procedure that suggests how to compute the weights. And in particular, once that the matrix is determined, the weights are given by the eigenvectors of the matrix, and let's not get into the details. And eigenvectors, which in eigenvector and eigenvalues. Eigenvectors in Italian are called autovettori and eigenvalues autovalori. This is something that goes back to our studies in matrix computation. I don't want to recall what are eigenvector and eigenvalues, so I give you, there are instructions to compute the weights, and it's just enough for me that you know that this procedure passes through the computation of eigenvectors and then eigenvalues, and the weights are the eigenvalues of this matrix that need to be rescaled in order they sum up to 1. Okay, so we compute the eigenvalues, and then we make sure that they sum up to 1. Okay, so let's first compute the weights, and then check consistency. I think the code is done is organized like this. First of all, here there is the definition of the matrix first. So I called it prova, which means trial in Italian. You can, of course, decide whatever names you like, whatever name you like. So, if I do like this, prova is a sequence of 0. And you know that in R, matrices need to be defined before using them. And then I assign the values. And as I said, the values that are assigned in my exercise are not the same that you see here. Okay. The values are, first of all, the diagonals. The diagonals are 1. And then there are the values in the pairwise comparison. And these values are defined by comparing each indicator with the others. And then I compute the symmetric ones, anti-symmetric is, okay? Which is, if I copy it in R, and then I look at the matrix, this is my matrix. Of course, I made sure, I say once again, that in the symmetric position, there is, if I have 9 here, there is 1 over 9 there, in the symmetric position. And if you look at the code, this is clear. I go back to the code. This is clear. You see that there is first the definition of each comparison and then the computation of the symmetric. So now I have my matrix. Okay. Now, here it's the computation of the eigenvectors. I copy it in R. And then I have to compute the eigenvalues. So here I already wrote an instruction which computes the eigenvalues and rescale them. So it's an instruction that gives to you already the value of the weights. And these are the weights. They sum up to 1. Now, if you look at these weights, they give the same weight to economics and fisheries. They give less weight to landscape, and the higher weight is given to tourism. So what will be the design flow that will be preferred, we still don't know, because remember that we have these utilities that have to be combined with the weight. And in particular, you see that tourism have a high weight, but the utilities are quite low for each of the alternatives. And the reason why the utilities are low is because tourism, the utility of tourism decreases very rapidly when we start withdrawing water. And this is why all the alternatives have a low utility. And therefore it may end up, we may end up with a situation where tourism, which has a high weight, is not really discriminating between these alternatives because the utility is very low in any case. But still, before computing, now we have the utilities of each alternative and each indicator and the weights. So it's very easy to compute the score for each alternative. It's very easy to combine this matrix and in particular the columns of this matrix with the weights that are given above. It's very easy. But before doing that, let's check consistency. Again, consistency checking requires a theoretical treatment that we don't inspect in detail. I just wanted to tell you that a necessary condition for the matrix to be consistent is that the max eigenvalue, is very close to the dimension of the matrix. The dimension of the matrix is, this is a matrix 4 by 4, and therefore I need to check that the max eigenvalue is close to 4. And what is the max eigenvalue? Should be this one. If I get this instruction here and I put it in R, should give the max eigenvalue. Let's see. Yeah, it's, you see that it's 4.04. which is quite close to 4, and what is a criteria for deciding, for taking a decision? Is it close to 4 enough or not? Now, there is a criteria which is based on the computation of a statistics, which is called here in the